Hello everyone. So in the last lecture that I uploaded, we studied about rank of a matrix which we denote as rank of A, right? So it was the maximum number of linearly independent rows or columns in a given matrix. In a matrix. Also, we studied that the order of the matrix, which is denoted as m cross n, where m stands for the number of rows and n stands for number of columns. So the rank should be less than minimum of m comma n. So suppose we have a 3 cross 4 matrix. So the rank of A should be less than equals to 3. It cannot be more than 3. So we discussed about how we can find through minors and then through elementary row operations. Okay, now moving forward, elementary row operations. Now we'll start with 14.3, section 14.3, which focuses on main results on linear systems of equation. This topic in general is very important. We'll do 2-3 questions related to it as well. Now suppose we are taking a scenario where there are, so in a system of equations, there are m simultaneous equation in n unknowns. So basically the variables are n variables and equations are m. So first equation, second, then mth equation, and x1, x2 till xn are the variables. So the A matrix would be the quotient matrix A11, A12 till A1n. Then A21, A22, A2n. AM1, AM2 till AMN. Okay. So the system of equations can be written in this form: AX equals to B. Now A is m cross n matrix. We can observe from here as well, m rows and n columns. Now A augmented B. So in the last class we have studied what A augmented B is. A augmented B, this can be written as the A matrix till A1n dot the right hand side, the B vector or the B matrix. This is B1. Then A21, A22, A2n, B2. Similarly till AM1, AMN, BM. So now the number of rows is still m, 1, 2 till m, but the number of columns have increased by 1. So this is a new addition. So the order is n plus 1. I hope so far this is clear. Now, the order of A augmented B is m cross n plus 1 and order of A matrix is m cross n. Now the number of rows are same, but if we see the number of columns, A has n columns, A augmented B has n plus 1 columns. So what we have is, because of these difference in columns, rank of AB should be always greater than equal to rank of A. We already know that rank would be minimum of this. So maximum linearly independent independent rows or columns and minimum of this. So minimum of m cross n plus 1. So basically minimum of m comma n plus 1 would be always greater than equal to minimum of m cross n. You can take m as 4, n as 3, so then it would be 4 comma 3. So this becomes 4 is greater than equal to 3. So you should know this. Okay, this is very logical in nature. And since only one column is being added, so the order is increasing by 1 only. So the rank of A augmented B cannot be greater than rank of A plus 1. Plus 1 because rank of A augmented B can be more than rank of A by 1 because this is due to the new column which is being added. Okay, now moving forward, theorem 14.3. So these concepts will become more clear once we start solving the questions. Okay, a necessary and sufficient condition for a linear system of equation to be consistent. A system of equation is consistent when it has at least one solution. तो बेसिकली अगर कोई सिस्टम ऑफ इक्वेशन के लिए हमें चाहिए कि सॉल्यूशन हो तो एक नेसेसरी और सफिशिएंट कंडीशन है दैट द रैंक ऑफ द कोफिशिएंट मैट्रिक्स इज इक्वल टू द रैंक ऑफ द ऑगमेंटेड मैट्रिक्स. बेसिकली अगर ये सिस्टम ऑफ इक्वेशन है इसका सॉल्यूशन तभी एग्जिस्ट करेगा जब रैंक ऑफ ए इक्वल्स टू रैंक ऑफ ए ऑगमेंटेड बी. It's a necessary and sufficient condition both. So double implication. तो basically अगर rank of A equals to rank of A augmented B है then in that case we know the system of equation would have a solution. It is consistent. The system of equation is consistent. By consistency we mean that it would have at least one solution. Then a system is said to be consistent. Repeating again, the system would have a solution, that is it is consistent if rank of A equals to rank A augmented B. Okay, now let's use this theorem to the following system of equation. This is the basic system of equation. So here the A matrix would be 2 minus 1 4 minus 2, B is 3 and 5. So A augmented B would be 2 minus 1 4 minus 2 3 5. So if they are equal then only the solution would exist. Now looking at rank of A, so it is 2 minus 1 4 minus 2. We'll use the operation R2 goes to R2 minus 2R1. So we have, this gives us 2 minus 1. So 4, this row would change. This would become 0 and then minus 2 minus of minus 1. This is plus 2. This would give you a value of 0. So we say there is only one row which is linearly independent. So the entire row is 0, which means the rank would get reduced by 1. So in this case the second row is 0, so the rank of A in this case is, the rank of A in this case is 1. Now rank of A augmented B, so we have 2 minus 1 4 minus 2 3 5. Using the same operation, R2 goes to R2 minus 2R1. We have, this fetches us 2 minus 1 3. Now this becomes 0, this becomes 0. So this becomes 5 minus 2 times 3, which is minus 1. Now look at this. This is very important. So the first equation can be written as 2x1 minus x2 equals to 3. Second equation can be written as 0x1 plus 0x2 equals to minus 1. So in this case, the rank of A augmented B is coming out to be 2. But now this system, so according to our theorem, since rank of A is 1, which is not equals to this, so the solution does not exist, or the system of equation is not consistent according to the theorem. Now we'll see, because of this we are having this thing. This equation is never satisfied. So we can see in this case the system of equations is not consistent. Okay, so we'll solve a few questions related to it, and then it would make things more clear. Okay, now moving forward. Now superfluous equations. I'll tell you what superfluous equations means. It means वो equations जिनकी जो हमारे पास अगर नहीं भी given है तब भी we'll get the same formula, same values for x1 x2. I'll give you an example. Suppose if we have 10 12 equation or even 3 4 equations, if one of the equation is 2x plus x2 equals to 5, and then another equation is 4x1 plus 2x2 equals to 10, you will see both these equations are giving you the same thing only, right? Suppose we have all these equations like 3x1 plus 20x2 equals to 1. Now what we can see is these two equations are giving you the same equation. This will fetch you the same equation. So we can say one equation is superfluous. That is, even if we don't use either this or this, because this equation B and this is suppose A, because B is 2 times A. So we can either use A or B and the other equation to find the solution. तो basically ये हमें extra दे रखी है, इसकी need नहीं है. तो this is what superfluous equation mean. Okay. Now suppose rank of A equals to rank of A augmented B equals to K, where K is less than M, where M is number of equation. So basically M equations है, हमारी रैंक आ रही है A और A augmented B की K, which is less than M. Now that would mean rank, we know the definition of rank. It means the maximum number of linearly independent rows or columns in the matrix. Now if the rank is coming out to be K, that means there are K linearly independent row vectors. Okay, I'll just show it here. Okay, so suppose we have A augmented B with us. A augmented B, A11, A12, then A1n, B1 till BM. Okay, so if we have this, now the rank is coming out to be K. So these are M equations. Suppose kth यहाँ पे आ रहा है, that would mean इस एलिमेंट पे one of the element is non-zero and इसके नीचे सारे elements are 0, right? Then we say there are K linearly independent rows, first, second, then third, fourth till kth, and rest all other elements after row operations would give you 0 value below this. So rank is K. Now if we have K linearly independent row vectors, that would mean the other row vectors like after k. So we have m minus k. तो बेसिकली ये जो बाकी रो वेक्टर्स बचे हैं, एक इक्वेशन, एक और इक्वेशन, बहुत सारी इक्वेशंस के वाले बचे होंगे, तो वी कैन express these row vectors as a linear combination of the first k vectors. So you should know the linear dependency and linear independency that we have discussed two classes back. So now this states that any other row vector in AB. So we have already talked about the k row vectors, and then the other remaining m minus k row vectors. This can be written as a linear combination of the first k vectors. I hope this was clear because these are superfluous equations only. So जो हमने इक्वेशन एक बार लिखी थी, अगर चलो ऐसे लिख लेते हैं, 2x2 equals to 5, then 2x2 plus 4x2 equals to 10. So what this means is एक इक्वेशन superfluous है एंड इसका जो सॉल्यूशन आएगा वो अपने आप इसको भी सेटिस्फाई करेगा. दिस इज व्हाट दे आर ट्राइंग टू से. ठीक है, सिस्टम सुपरफ्लुअस तो है इक्वेशंस, बट उसका सॉल्यूशन बाकियों को भी सेटिस्फाई करेगा. सो इफ दिस वेक्टर सेटिस्फाइज द के इक्वेशंस, then it will also satisfy any other equation corresponding to a row in AB. Corresponding to a row in AB, because we know any row in AB other than the first k rows is a linear combination of the k rows only. तो स्टार्टिंग की k rows तो हो गई, उससे सॉल्यूशन निकला हमारा x1 x2 xn करके, एंड रिमेनिंग m माइनस k rows है, दे आर अ लीनियर कॉम्बिनेशन ऑफ द k वेक्टर्स. तो ये सॉल्यूशन जो निकला वो इसको भी सेटिस्फाई करेगा. ओके, आई होप दिस वॉज क्लियर. See, okay, we'll do some questions related to it as well. So first let's do the theorems. Now coming to theorem 14.4. Suppose that system of equation has solutions. So it has solution when rank of A equals to rank of A augmented B, and that the common rank equals to k is less than m. So we have already discussed this is less than m. Then there exists m minus k of the equations that are superfluous. हमने डिस्कस करा रिमेनिंग सुपरफ्लुअस हो गई, in the sense that any solution that satisfies the other k equation will also satisfy these m minus k equations. because जो m minus k equations है वो भी तो linear combination है k equations का. They can be written as a linear combination of k equations. तो अगर वो लीनियर कॉम्बिनेशन है ऑफ के इक्वेशंस का, तो अगर जो x की वैल्यूज़ जो हम सॉल्यूशन आ रहा है वो के इक्वेशंस को सेटिस्फाई कर रहा है, तो वो m माइनस के को भी सेटिस्फाई करेगा. सो बेसिकली तो जो सुपरफ्लुअस इक्वेशंस है तो हम उसको इग्नोर कर सकते हैं वाइल सॉल्विंग द सिस्टम. आई होप दिस वॉज क्लियर. नाउ moving to degrees of freedom, theorem 14.5. Now we have discussed there were m equations and n variables, and the rank was a, so rank of a augmented b, which was equals to k. Now the theorem states that, so we'll do some questions related to it as well, and that would actually boost the confidence. Okay, suppose the system of equations has solutions and that rank of a equals to rank of b equals to k, which is less than n, the number of variables present in the system of equation. Now then there exist n minus k of the variables that can be chosen freely. अगर रैंक k आई है, टोटल वेरिएबल्स n है, वेयर n इज ग्रेटर देन इक्वल टू k, देन n माइनस k जो रिमेनिंग वेरिएबल है दे कैन बी चूजन फ्रीली. उनको कुछ भी वैल्यू लोगे, ये द फर्स्ट k वेरिएबल्स वुड बी यूनिकली डिटरमाइंड. बाकी बचे हुए उनको कुछ भी ले सकते हैं. We'll see this in the question that we'll do. Now, whereas the remaining k variables are uniquely determined by the choice of the n minus k free variables. तो जो हम फ्री वेरिएबल्स की वैल्यू लेंगे अकॉर्डिंगली ये k वेरिएबल यूनिकली डिटरमाइन होंगे. सो वी से दैट द सिस्टम हैज़ n minus k degrees of freedom. When we are talking about degrees of freedom, we need to consider the rank of A and rank of A augmented B and compare it with compare it with the number of variables present in the model. So n minus k gives you the degrees of freedom, whereas when we were talking about superfluous equations, we talked about m minus k. So the remaining equations. Okay. Now, okay, I'll be helping you in this question. So let's start with the. Okay, we'll do 3 questions. Let me do the first one and I'll ask you to do the other by yourself. Decide whether the following system of equations has any solution, and if it has, find the number of degrees of freedom. So we know it would have a solution when rank of A equals to rank of A augmented B, and that can be any value when both of them are equal, right? Now we'll solve rank of A augmented B, and with this help we'll be able to find the rank of A as well. And if it has, find the number of degrees of freedom. So we know degrees of freedom would be n minus k, where k is the rank. Now firstly, what is n? The number of variables. So in this case, x1, x2, x3, x4, x5. So n is 5. We know this so this is given. So our A augmented B matrix would be written as 1, 1. So writing these quotients, 1 into this, 1 into this, minus 2 into this, then 1, then 3. Augmented 1, 2, 3, 3. And this is 2, minus 1, 2, 2, 6, 3, 5, minus 10, minus 3, minus 9, 3, 2, minus 4, minus 3, minus 9. Okay, now the row operation that we'll use is R2 goes to, so we'll make this as 0, all these terms as 0. So this would go R2 minus 2R1. I'm using this simultaneously. R3 goes to R3 minus 3R1, and R4 goes to R4 minus 3R1. So the first row would remain same, augmented 1. Okay, this would become 0, minus 1, minus 2, this is minus 3, 2 plus 4, this would become 6, 2 minus 2, 0, 6 minus 3, 0. This is also 0. Now 3 minus 3, 5 minus 3, 2, minus 10, plus 6, minus 4, minus 3, minus 3, minus 6, minus 9, minus 3, minus 18, 3 times minus 3, this would be 0. Similarly, this would be 0, 2 minus 3, minus 1, this would be 5, 3, okay, minus 4, plus 6, this is 2, minus 3, minus 3, minus 6, and the last one would be minus 9, this is minus 18 only, this would be 0. Okay, now we can use the operation R2 goes to minus 1 by 3 R2. This will make this as 1 and this as minus 2. So I'll just erase it here. So we'll make it as 1 and this will make it as minus 2. Now we'll use the operation Okay, we have enough space. Use the operation R2 goes to, sorry, R3 will make them as 0 with the reference of this. R3 goes to R3 minus 2R1 and R4 goes to R4 plus R1. So we have 1 0 0 0 1. So the thing is, first row won't change and the right hand side here also won't change because it consists of 0 only. 1 minus 2 0 0 0 minus 4 plus 2 0 minus 6 minus 2 minus 8 minus 18 plus 3 minus 15 0 0 minus 5. Okay, I'm not sure, this is minus 15. I'll just verify it. I have solved this, whether I'm getting the same values or not. So this is minus 1 2, this is fine. Okay, so this value I have made a mistake. Okay, so this is not R1, this is R2 with reference to this. So this would be R2. So this would be minus 6 only, minus 18 and minus 6 minus 18. Now the fourth row can be written as R4 goes to R4 plus R3. Now we have made this one. I'll move in this direction. If this is 0, we'll move in this manner. You need to remember this. We'll move in this direction, make this as 1. So we'll use, before this, we'll use R3 goes to minus 1 by 6 R3. So this would become 1 and this would become 3. So this becomes 1, this becomes 3. Now R4 goes to R4 plus 6 R3. So the final matrix that we'll get is 1 1 minus 2 1 3 augmented 1 0 0 0, then 0 0 0 1 0 0 minus 2 0 0 0 0 1 3 0 0. Now you will see, if you're talking about, this is first, second, and since it is 0, we'll move in this section, third. So the rank is 1 2 and 3. It would be 4 if this would have been a different number. So now if we talk about just A matrix, rank of A is coming out to be 3. Had it been the case that this 0 was a number, suppose x1, which is not equals to 0. Sorry, not x1, let's take it as A, which is not equals to 0. In that case, rank of A would have been 4. But now we have seen it is coming out to be 0. So we'll move now to check the rank of A augmented B. This is already 0 rank of A, and if this element is not equal to 0, then rank of A augmented B would be 4. But in this given case, rank of A augmented B is 3 because this is also 0. So we have 3 independent rows only. So we know the solution would exist. Now talking about degrees of freedom. Now writing this system of equation, what we have is x1 plus x2. So 1 times x2 minus 2 times x3 plus 1 times x4 plus 3 times x5 is 1. With the help of this, we know this is 0x1 plus 1x2 minus 2x3, and this is 0 0 equals to 0, right? Now similarly this gives us x4 plus 3x5 equals to 0. Now talking about degrees of freedom was calculated as n minus k, where n were the number of variables. Now 5 variables we have, x1, x2 till x5, and k is rank that we have found as 3. So degrees of freedom are 2. So this means any two variables we can take to be arbitrary numbers and the rest would be uniquely determined. So suppose if we take x2 equals to a, any arbitrary number, and x5 equals to b. We can take any other number. Suppose we are taking x2 as a and x5 as b. Now these are arbitrary. So what we can the degrees of freedom suggest is, since these are arbitrary, but for any given fixed value of x2 and x5, we'll have some unique values for x1, x3 and x4. Now with the help of, suppose this is C, this is B, this is A. Now suppose with the help of equation C, what we have is x4 plus 3x5. So x5 is b, 3b equals to 0. So this implies x4 gives us a value minus 3b. This is the value of x4 that we're getting. Now using the b equation, we have equation b, we have x2 equals to 2x3, and since x2 was a, so a equals to 2x3. So this implies x3 equals to a by 2. So we have found the value of x3 as well. x2, so only x1 is left. So with the help of equation first, we have x1 plus x2. So x2 was a, x2 is a, x5 is b, minus 2x3, 2 times a by 2 plus x4. x4 was minus 3b plus 3x5. 3x5 was b equals to 1. So this cancels out, 2 to cancel, minus a. So we have x1 equals to 1. So if we take x2 equals to a and x5 equals to b, we are getting x4 equals to minus 3b, x3 equals to a by 2 and x1 equals to 1. So these are the degrees of freedom are 2. So x2 and x5 can take any random value, and then subsequently the other 3 variables would be dependent on the values of x2 and x5. So we have chosen x2 and x5. We can choose any other value that would give you the same result. Now okay, so we have 2 questions. Okay, let's start with this one. Prove that the system 2x plus 3y equals to k and x plus cy equals to 1 has a unique solution. So it would have a unique solution when rank of a equals to rank of a augmented b, and this is equals to, so if it is a unique solution, this should be equals to n, because जो हमने पढ़ा था वो अगर k है, k से, and if k is less than n, तो n minus k फ्री वेरिएबल्स हो जाएंगे. फ्री वेरिएबल्स हो जाएंगे तो उनकी वैल्यू जैसे तुम चेंज करोगे आंसर भी इन्फिनाइट आ जाएगा. तो इस केस में यूनिक सॉल्यूशन तब पॉसिबल है जब दोनों की रैंक इज इक्वल्स टू n. So has a unique solution except for one particular value c star of c. Find this solution. Prove also that for c star equals to c, the system has no solution except for a special value k star of k. Find the solution for k star equals to k. So I've read it very fast. I'm giving you at least 4 minutes to solve this, and I expect, so it is 220. I'll start at 224. So you try to solve it on your own. Okay. Now the A augmented B matrix can be written as 2, 3, the quotient of x is 1, the quotient of y is c, dotted line, then k, 1. Now, so we'll make this as 0, or we can make this first as 1. It will help in solving the r1 goes to 1 by 2 r1. This gives us 1, 3 by 2, k by 2, 1 c 1. Now need to make this as 0, this as 0. So r2 goes to r2 minus r1. So A augmented B becomes 1, 3 by 2, k by 2. This becomes 0. This becomes c minus 3 by 2. And this becomes 1 minus k by 2. Now what we are supposed to show, that it has a unique solution. except for one particular value C star of C. Now it would have a unique solution when rank of A equals to rank of A augmented B equals to 2. N is 2 in this case. And look at this. If this comes out to be 0, then rank of A would be 2. Sorry, rank of A in that case would be 1, because the entire row would be 0 in that case. So rank of A would come out to be 1. But if this doesn't come out to be 0, then rank of A augmented B would be 2. In that case, the solution does not exist. Okay, so we'll start with what they are asking. So has a unique solution except for one particular value C star of C. So if this is not 0, okay, if this is not 0, then we will have a unique solution. So C minus 3 by 2 should not be equals to 0. In that case, if this is not 0, we will have rank of A as 2 and rank of A augmented B, and this would be equals to rank of A augmented B. So the solution would be unique. So when C is not equals to 3 by 2, we'll have a unique solution. And find this solution. So C star value is 3 by 2. So when C star is not equals to 3 by 2, we'll have a unique solution. And the value of the solution would be, this would be equals to 1 minus k by 2. So this times x2, x or y. Sorry, this is not x2, this is y. So what we have is y times this equals to this, 2c minus 3 equals to 2 minus k upon 2. So this 2 cancels out. So we have the value of y as 2 minus k, 2c minus 3. And accordingly, if we substitute this back into this equation, we'll get the value of x as well. Now the question is asking, prove also that for C star equals to C, the system has no solution except for a special value k star of k. Now I'm writing the A augmented B matrix again, and I'll tell what they are asking. 1 3 by 2 k by 2 0 c minus 3 by 2 and 1 minus k by 2. Now what they are asking is that एक C star equals to C जो हमने निकाला था, जो हमारा C star 3 by 2 आ रहा था, तो उस वैल्यू पे भी the system has no solution except for a special value k of k star. Find the solution for k equals to k star. Now अब अगर C equals to 3 by 2 है, so this value would become 0. So our A augmented B matrix is 1 0 3 by 2 0 and then k by 2 1 minus k by 2. And if this is not equals to 0, so if 1 minus k by 2 is not equals to 0, that means k is not equals to 2. If k is not equals to 2, in this case we have rank of A. तो A की तो second row is totally 0. तो rank of A is 1. Whereas rank of A augmented B would be 2 if k is not equals to 2. And since ये दो ranks equal नहीं है, तो solution does not exist. Okay, but the solution would exist and it would be an infinite solution when this term also becomes 0. So in that case, rank of A would be equals to 1, which would be equals to rank of A augmented B. So this is possible when 1 minus k by 2 is 0. This means when k is 2 and c was 3 by 2, we would have, in this particular case, when k is 2 and c is 3 by 2, we would have rank of A equals to 1 equals to rank of A augmented B. And that would suggest that degrees of freedom. So degrees of freedom is n minus k, where k is rank. So n is 2, 2 minus 1, 1. So this suggests that one of the variable can take any value, any arbitrary value. So we have this equation left with us. So x plus 3 by 2 y equals to k by 2. Now if, so in this particular case k was 2, so this is 2 by 2, so 1. So we have the equation x plus 3 by 2 y equals to 1. Now what does that mean? If you take any value for y, accordingly you can get a unique value for x. Since, and very logically, two variables and only one equation. So in this case, you will have infinite solution. So in this particular case, when this happens, that you will have solution. So this k star was 2, this c star is 3 by 2. Okay, you can expect these types of questions coming in the exam. One more question is left, we'll do that as well. It is 232. So you need to discuss the solutions of this for different values of a and b. So I'll again give you, it's 232, I'll give you time till 237 to solve this on your own. I would prefer you to solve this on your own, because in exam you might get a question, so you'll get habitual to it. So try solving this on your own. This is x plus 2y plus 3z equals to 1 minus x plus ay minus 21z equals to 2, 3x plus 7y plus az equals to b. So you need to tell about how, whether the solution would exist, and even if exist, whether it is unique or infinitely many. So you know in which particular case this would be, and whether no solution exists. So you need to find the rank of A augmented B. So I'm giving you time till 238 to solve this, and then I'll solve it. start solving it. Write down the A augmented B matrix and then use the elementary row operations, the diagonal elements, and make the below entries 0. Try to make them as 0. Okay. Now what we have seen is the A augmented B matrix. This can be written as 1, 2, 3 augmented 1 minus 1 A minus 21, then 2, 3, 7 A and B. So this is the A augmented B matrix. Firstly, a unique solution would exist. So now here n is 3 variables. A unique solution would exist when rank of A, you're talking about unique solution, it would exist when rank of A equals to rank of A augmented B equals to n. In that case, a unique solution would exist. And infinite solution would exist when rank of A equals to rank of A augmented B equals to k, which is less than n. That would lead to n minus k degrees of freedom as well, which we have discussed. And there would be no solution when rank of A is strictly less than rank of A augmented B. So whatever rank of A would be, the rank of A augmented would be, suppose it is k, so rank of A augmented B would be k plus 1, because it is only one column which is being added, so rank can increase by a maximum of 1. Now solving this, we'll use the operation R2 goes to R2 plus R1 and R3 goes to R3 minus 3R1. So this would give us the value A augmented B would be 1 minus 1. Sorry, this would be, I'll write the row first. This would be 1, 2, 3, 1. Now this would become 0. This would become A plus 2. This would become minus 21 plus 3 would give you minus 18. 2 plus 1, 3. Now 3 minus 3 times this would 0. 7 minus 2 into 3 is 1. This would be A minus 3 times 3, A minus 9. And this would be B minus 3. So far we have this. Now we'll use the row operation. We'll make this as 1 to simplify our calculation. R2 goes to 1 by A plus 2 R2. So the matrix that we'll get is, so A augmented B in that case would be 1, 0, 0. This is 2. The first row would remain same only. 1. This would become 1. Then 18 upon A plus 2 minus 18 upon. Then 3 upon A plus 2. Then 1. A minus 9. B minus 3. Now the last row operation that we'll use is, we'll make this as 0. So R3 goes to R3 minus R2. The A augmented B matrix that we'll get is 1, 2, 3, 1. This is 0. This is 1. This would remain same only. A plus 2. 3 upon a plus 2. Now 0, 0. This term would become a minus 9 minus of minus 18 upon a plus 2. So this becomes a minus 9 plus 18 upon a plus 2. So I'm simplifying it here only. So this becomes a minus 9 a plus 2 plus 18 upon a plus 2. So if we'll solve this, this is a square plus 2a minus 9a minus 18 plus 18 upon a plus 2. So this cancels out. So we have a square minus 7a upon a plus 2. So this can be written as a into a minus 7 upon a plus 2. We have solved here. Okay, the right hand side. So this would become b minus 3 times a plus 2. Okay, so we'll leave it at here only. B minus 3 minus of 3 times a plus 2. Now, no solution. Now, let's talk about the case of no solution. So, no solution would exist when we have rank of A strictly less than rank of A augmented B. So, in this case, 1, 2. Now, rank of A, this is possible only when rank of A is 2 and rank of A augmented B is 3, which means this term should be 0 and this term should not be 0. Okay, so this term is 0 when A is 0 or A is 7. So we have seen if A is 0 and A is 7, this term is 0. Right? So no solution would exist when this is 0. So that rank of A is 1 and this is not 0. So if suppose A is 0, so this term should not be 0. This means B minus 3 upon A plus 2, so 0 plus 2 should not be 0. So B minus 3 by 2 should not be 0. So B minus 9 by 2 should not be 0. So B should not be equals to 9 by 2. So if A is 0 and if B is not equals to 9 by 2, then we have a case of no solution. Similarly, when A equals to 7, then B minus 3 upon 7 plus 2 should not be 0. So B minus 3 by 9. So this would cancel out 1 by 3. So 9. So B minus 10 by 3 should not be 0. So basically B should not be equals to 10 by 3. So the second case is if A is 7 and if B is not equals to 7 by 3, then we will have no solution. Similarly, there would be infinite solutions. There would be infinite solution when we have this term as 0 and this term as well to be 0. So that would be when rank of A equals to rank of A augmented B, and that is equals to K, which is less than N. So in this case, this is equals to 2, which is less than 3. So it would be possible when A is 0 and from the above case itself B is 9 by 2. Similarly, first case second, A is 7, B is 10 by 3. And now a unique solution would exist. Now the last case of a unique solution. A unique solution would exist when rank of A equals to rank of A augmented B, which is equals to 3 in this case. So when this is not equals to 0, which means A is not equals to 0 and A is not equals to 7. And in that case, so even if this is 0, it won't matter. This will give you the exact value. So if this is 0, so x1 and x3 could be 0. So okay, so A is not equals to 0 and B is not equals to 9 by 2 corresponding to this, and B should not be equals to 10 by 3. So this is how you are supposed to write the answer. Like you need to show these calculations as well, all of them, and you need to write in a very systematic manner. So with this, we have completed 14.3. Let me know if you want to solve more questions related to this. So I'll post it, or else we'll move to 14.4, which is eigenvalues and eigenvectors. So we are left with 14.4 and 14.5, and with this we'll be done with chapter 14 as well. 14.6 is not a part of your syllabus. It has been removed. So last year also it was not a part of the syllabus. So we are left with 14.4 and 14.5 only. But let me know if you face any problem or you want more questions to be solved on this. So that would actually boost your confidence, and then accordingly we'll move to 14.4. Okay, thank you.